Hi, my name is Hana G, and I'm a PhD student of the University of Edinburgh. The title of this presentation is Quantifying Sound Graphic Systematicity in Multiple Phonographs. My project is quite interdisciplinary, including psychology, linguistics, and computation. Let me introduce our approach to this issue first. Complex system consist of a large number of elements, and there are vigorous interactions among those elements. As a result, dynamic, unpredictable, and non-linear pattern is observed. Let's take our body, for example. Our body consists of different subsystems. Imagine you're being chased by a large dog. Your respiratory system and circulatory system become very busy to deliver fresh oxygen to your muscle. The other systems, less important at that moment, will hold their activity until the emergency ends. This example shows how subsystems work in harmony within a larger system in order to achieve the ultimate goal, which is maintaining the integrity of the whole system. We define systematicity as the controlled cooperation between these subsystems. Language is also a complex system. Studies found systematic relation between phonology and syntax or between phonology and semantics. Comparatively scant research was done between phonology and orthography, mainly due to the status of written language as less important subsidiary information to the main spoken language. Many hypotheses were proposed in this regard, but they are largely based on subjective, somewhat Anglocentric presumptions like letter O represents our mouth shape and letter S represent the sound of snakes. We instead suggest more objective method to investigate the systematicity between phonology and orthography. In terms of method, I measured all the pairwise distances between letters and all the pairwise distances between the corresponding phonemes, and I examined the correlation between these two lists of distances. The first question you might ask is how we measure the distance between phonemes. I used the features from the International Phonetic Alphabet, so-called IPA. It defines phonemes according to the place of articulation, the manners of articulation, and whether it is voiced or voiceless. For vowels, we considered the location of the tongue, roundness, and openness of the lips. We aligned those features in a line and simply marked which features the phoneme has. In this way, we were able to transform the phonemes into binary vectors. Then the distance between phonemes equals to the distance between vectors. The distance between vectors were measured by many different ways. Featuretic distance simply counts how many different features are there between two vectors. Euclidean distance measures the shortest geometric spatial distance. The dimension of the space equals to the length of the vectors. So in this case, 22 dimensions, which is impossible to visualize. For Jacquard distance, the number of shared features is divided by the total number of features. Cosine distance measures the angles between the vectors. The next question you might ask is how we measure the distance between letters. Before I continue, I'd like to introduce what inspired me to quantify the visual distance between letters. Hangeul, the Korean writing system, was artificially made in the 15th century by the king and his scholars. Korean consonants visualize articulation or kinesthetic movement. For example, the first picture, g, represents the tongue touches the soft palate, and the fourth picture, s, represents the airflow through your teeth. But more importantly, in connection with the systematicity, Korean has visual consistency between letters and phonemes. For example, the basic sound g, if you add one more line to it, it becomes aspirated sound k, as in key. And if you duplicate it, it becomes tensed sound g, as in sky. This tendency is observed across the other consonants. So I try to quantify the distance between letters based on this regularity for Korean first. I collected all the lines that Korean letters can have. This is only for the consonant, but I also did it for vowels. I gave a name to each line, and then by simply marking which lines a letter has, I can encode the letters into binary vectors. The distance between two letters now equals to the distance between two vectors. I name this method stroke share rate. I'll quickly show you the result. This is the correlation between phonological distances and orthographical distances of Korean language, measured by stroke share rate. Korean letters overlap their pronunciation by 50 to 70% depending on the metric. This high sound letter correlation was somewhat expected considering how they were constructed. Apparently, I'm not the only person who came up with this idea. One previous research measured the difference between English letters based on the overlapping geometric features, but they worked only on English uppercases. So I additionally designed myself the features of the lower cases as this sparse matrix. I try to be objective and systematic as much as possible, but I was not able to escape absolutely from the subjectivity. And I'm not sure how strongly other people would agree with this classification. Another problem of this stroke rate is that this method is not efficient to apply to other phonographic orthographies. What I wanted was the method I can apply consistently to other orthographies so that we can compare the letter sound correlations. As an alternative, we applied Hausdorff Distance. Hausdorff Distance measures the similarity between two images. It compares one point of an image and the identical point of the other image. If they don't match pixel-wise, it instead measures the Euclidean distance with the nearest black pixels. Because the letters are analyzed as images, different fonts return different values, as you can see in this table. Therefore, we tested multiple fonts available from Microsoft. For example, for English, we tested 29 different typefaces. Including English, in this way, I examined some other conventional orthographies like Arabic, Cyrillic, Finnish, Greek, and Hebrew, mostly from Semitic languages. 4 ancient orthographies, Phoenician, Nabatean, Early Arabic, and Aramaic were also examined. 2 fictitious orthographies, Aurebesh from Star Wars and Klingon from Star Trek were included as well. A fun fact about Aurebesh is that the name Aurebesh came from the first 2 letter names, Aurak and Bash, just like the name alphabet came from the first 2 letters, alpha and beta. A possible question here would be how we chose which phonemes to use for English, because English letters are connected to multiple sounds, especially for vowels. We followed the phonics approach that aims for one-to-one connection between letters and sound of English. This is how they teach children alphabet. For example, letter A is connected to sound E as in ant only. And letter I is taught as E sound only over other alternatives. In this way, we could limit the range of phonemes. Now the result. First of all, this graph shows the distribution of all the correlations from all the fonts of each orthography. Here, y-axis here means the number of the fonts that return the same correlation coefficients. This widely distributed pattern here is Korean. I examined 89 different fonts in Korean, and most of them returned positive correlations. In general, it shows the letter sound correlation is basically arbitrary, close to zero. However, I have to say that the recent studies of linguistic systematicity mainly deal with very small coefficients. For example, the sound meaning systematicity of English is 0.03. And the word form, meaning systematicity of English, is 0.001, very small. As expected, Korean returned the significant positive sound letter correlation. The positive correlation means that similar letters tend to have similar sounds. Surprisingly, significant correlation was found in the other conventional orthographies as well, although the coefficients were lower than Korean. The fact that limiting English sounds returned significant correlation has some pedagogical implication. Greek lowercase uniquely returned the negative sound letter correlation, which means they evolved in a way that similar letters have different sounds, or vice versa. I expected the ancient orthographies to demonstrate increasing letter sound systematicity as time goes on, to argue that orthography has evolved in the way to maximize the systematicity with the sounds. However, unfortunately, none of them return robust results. One of the insights is that the consistent orientation of the letters may contribute to the systematicity. For example, in Phoenician here, each letter has its own orientation, which resembles Klingon actually. Limited choice of the typefaces of the ancient letters was another disadvantage. No systematicity was observed from two fictitious orthographies. We conducted Monte Carlo permutation test for verification. I randomly paired phonological distances and orthographical distances and calculate the correlation coefficient. By repeating this procedure for 10,000 times, we could accumulate these coefficients, as you can see, as boxes in these graphs. If the veridical coefficient, which is the red dot, is located within the box, it means that the correlation we found is nothing but chance level. This red dot far from the box means that what we found is significant. For example, compare with Arabic. The red dots are far from the boxes, which means the result is statistically significant. So we can say that Korean can provide the golden standard of sound letter systematicity, whereas these fictitious orthographies can be the baseline. Some fonts returned stronger systematicity than others. Here are some cases for Arabic, English, and Hebrew. For other orthographies with Roman alphabet, Korean consistently demonstrated high significant correlation. For more details regarding methodology and results, please refer to the preprint we uploaded under the same title with this presentation. What mechanism lies behind systematicity? A good demonstration of a possible mechanism comes from two English shorthand systems, Shavian alphabet and Pitman shorthand. They both returned significant correlation as high as Korean. Shavian alphabet was designed by George Barnard Shaw. As you can see, he designed the voiced and voiceless sound pair visually systematic. They are identical shapes but oriented in the opposite direction. This resembles how Korean consonants were designed, where the triad set of voiced, voiceless, and tensed sound are visually consistent. Pitman shorthand provides an additional insight. If you compare the coefficients again, Pitman shorthand returns lower and weaker correlation than Shavian alphabet. Pitman shorthand also has systematic voiced and voiceless phoneme pair, but it distinguishes them by the thickness of the lines only. This indicates that the whole letter sound systematicity can be disturbed and decreased if the letters look too similar to each other. One possible and very important criticism from the psycholinguistic perspective is that these methods concern too much low-level perception only. The current understanding of cognition is based more on the predictive model, where the brain actively makes a choice of the stimuli so that it can sculpt and refine the model of the world. I'd like to leave it to my future research for now, but I think it is necessary to evaluate our method compared to the data from a higher level letter recognition, for example, confusion matrix. Confusion matrix is the result of human behavioral study, where participants judge the letter they are seeing. The letters are usually degraded with a lot of noise, so it is difficult to see clearly what letter it is. Therefore, as you can see, the probability of judging letter A as A is below 1. It's only 0.58. The experiment looks for the probability of other letters it is confused with. So if you see when the letter A is represented, it is mistakenly perceived as K by 10%. We compared our Hausdorff data with 4 different confusion matrices and found medium level of correlation between 2, which means the low level and high level letter recognition data overlaps by 50%. But I should also say that the correlation among those confusion matrices is about 0.5 as well. They agree to each other by 50% maximum, mainly because of the slightly different experiment design. So here I'd like to argue that our low-level Hausdorff data can explain the letter recognition as much as any confusion matrix can. Our MSc students additionally found interesting aspects in the letter sound systematicity. First of all, Dipao analyzed the English font, adjusting pixel-wise, and found that thicker stroke and wider character increased the sound letter correlation of English. This means the orthographic change corresponds to the phonological change. Second of all, Du found a negative sound letter correlation in Chinese pictographs, but in the early acquired characters only. This systematicity disappears so quickly that the characters acquired in the second year didn't return any result. Finally, Jiang also found that Chinese sound letter correlation decreases as the stroke gets thicker, which is the opposite from English. In conclusion, I found a small but significant letter sound systematicity in some conventional orthographies, but not in the fictitious ones. I'd like to summarize this presentation by emphasizing why such a systematicity is important for a language. Our brain is a surprisingly efficient organ and naturally maximizes the systematicity. For language, such systematicity has been observed in different levels and different aspects. The current study focused on the relation between letters and sounds because letter-sound connection matters. Obviously, Literacy rate is closely related to a country's socioeconomic status, but it doesn't always agree with it. For example, Georgia ranks 15th in the literacy rate list, whereas UK 49th. We argue that orthographic depth may play a role here in the case of unexpectedly low literacy rate and a high population of dyslexia, which is actually supported by many studies. Georgia is one of the shallowest orthographies, but where letter sound connection is transparent and consistent. But English, as you know, is notorious for its deep orthography. According to some research, it is deeper than German or French. One researcher even called it dyslexic orthography. In fact, if you fail to building correct letter sound connection, you are more likely to experience difficulties in reading. What do our findings imply in this regard? Some fonts return more robust systematicity than other fonts. We suggest that using these typefaces may contribute to building solid letter sound connection, especially for children who begin learning to read or people with certain type of dyslexia. Our brain will pick up and exploit this systematicity, however small the effect size is. This is the end of the presentation. Thank you for listening.
Thank you. So we have a question by Dan Harbour.
Hi, this is fascinating. I wish I'd known about your work last year when I was writing a chapter. So first, a plea for you to look at Bell's visible speech, which is the only system I know of that is aims to be at least as systematic as Korean.
All right.
I'd be really curious to see what results you come up with. Then a more contentful question is, the features that you assume for nouns and verbs, for consonants and vowels that you then build into your distance metric, was I right in thinking that the features are completely disjoint for consonants and vowels, that there are no, so there are shared features?
Yes, there are shared features. It's very simple. You can just elongate the vectors. The first part is consonant part, and the second part is vowel part.
I mean something different though. For instance, the feature back, is that a feature of consonants and of vowels?
Oh,
or is it just
back?
Yeah.
Back is a vowel feature.
Okay. Is that, how much would your results change if you assumed that, so for instance, there are very well-known vowel consonant interactions and phonotactic constraints, like ki in many languages becomes chi, or si or tsi or something like that. And it's because they both exploit the same place of articulation. But in a feature system where vowels have one set of features and consonants have another one, that correlation won't come out. So I'd be very curious to know if you have a feature system that's built to capture those kind of interactions, how the distance metric changes.
Well, is it interaction between vowel and consonant? I think it's just a matter of the difference in manner of articulation. The place of articulation is the same, but manner of articulation is different, like whether it is plosive or fricative.
Plosive. Shifting. So for instance, a velar will become a palatal, a dental will become a palatal, or else you'll get switching, so a dental can become a velar.
You mean like in Spanish? Like C sounds sometimes.
Yeah, so Romance on the whole, but this is very common cross-linguistically.
Right. This problem is not included because I had to limit the range of phoneme. So, for example, if I dealt with Spanish, C is supposed to have one sound only, so I had to choose. So these interaction between consonants and sound are not yet included.
Okay. I'm not quite getting the question across, but maybe we should talk offline and I'll pass over something else. But thanks very much, really fascinating.
Sorry.
Okay, thank you very much.